All right, so for an example of calculating sample size when the population standard deviation is unknown, we're going to return to this problem with Sprint and T-Mobile um, data speeds in various airports. Now, last time, we had a sample size of 5 airports. So actually, let me just go ahead and read the problem here. So in the previous think pair share, we had a 95% confidence interval that we calculated for the data speeds of Sprint and T-Mobile with a sample size of 5. The byproduct of a small sample size produced large margins of error for both Sprint and T-Mobile. So remember, the margin of error for Sprint was 14.23 and T-Mobile was 7.32. What we want to know is what sample size would one need to produce a confidence interval with a margin of error of at most 2? So now we want to have a margin of error of at most 2, not 14 and not 7, but 2. How can we narrow down um, the average speed in an airport, and do it with a 95% confidence level? So we're going to provide both a rough estimate and a better estimate of sample size. Okay, so we're going to be doing 2 sets of calculations side by side. Yeah, I'll go ahead and we're going to do calculations for Sprint, and I'll try and see if I can use this other color for T-Mobile. All right, now to do a rough estimate, actually, we'll keep doing this. This could take too long. Let's see here. All right, so for a rough estimate, we're going to be using the normal distribution. So we're going to calculate sample size using a normal distribution. That's what the z means there. So we need to use this equation of z alpha 2. Now, we don't have the population standard deviation, so we're going to use the next best thing, which is the sample standard deviation, and divide that by our margin of error. And we're going to square that. And what we were told is that we want a margin of error. We want to design a margin of error to be at most 2. Okay. All right. And let me write the same thing down over here. So we need a sample size. That's going to be from the normal distribution. So we've got z alpha 2 times s divided by e. That'll be squared, and the error, margin of error, is going to be equal to 2. All right. But what we need to do is to go ahead and calculate this z alpha 2 score here. So to do that, I'm going to go ahead and make a normal distribution now. We want to have a confidence level of 0.95. And we're going to have a significance level divided by 2. So 0.05 divided by 2 is going to be 0.025. In each of these tails. And we want a z critical value. Now remember, we're doing a normal distribution here because it's the best we can do. can't use a student's t because for student's t you need degrees of freedom, and degrees of freedom need sample size. We don't have it. We're trying to figure out what the sample size is. All right, so now we just need to use an inverse distribution function to convert this area into a positive z-score. Um, so let's go ahead and do that. And let me clear that. Okay. So I want to use inverse norm, an area of 0.025 with a mean of 0, standard deviation of 1 to the right. Okay. So 1.959. And I'm going to go ahead and store that into variable z. So I'm going to hit alpha 2. There we go. And then over here with numworks, I go ahead and clear this out. And I want to go home, go to the distributions function. Let me back out. I want a normal distribution now with a mean of 0, standard deviation of 1. And I want the area to the right and an area of 0.025 like that. All right, and I will save this value also to variable z. There we go. Okay, so we got 1.960. So let's see, this is Z critical score, 1.960. All right, so what we're going to do is we're going to plug in 1.960, and we ended up putting that into capital letter Z on the calculator. Now our standard deviation, let me write all this down here before I move on. Okay. Sorry, this toolbar is getting in my way. Okay. So what was the sample standard deviation? So we need this from the previous example. And hoping, let's see, do I still have that left over? You look at my variables here. Let's see, does it have? No. Okay, well, let's check and see. So the best way to check and see is just to put this in, see what it is. 11.464. So that looks right. All right, so I think that the other standard deviation is going to be in here as well. So to calculate this for sprint, it's going to be our z value times the standard deviation divided by 2 and all that squared. So I'm going to put parentheses. Oh, there we go. Okay, so I'm going to put parentheses, parentheses again, and then got z times this standard deviation. So I'm going to hit variables, statistics, Now I don't have to arrow down and hit enter. I could have just hit the number 3 like this, and it'll put it there. And then that's going to be divided by 2. That's my error. And then I want that squared. All right. And I think on the numworks calculator, I put that value in capital S. So let me make sure that that's still present. Yep, it's still there. Um, so let me type the same thing. So parentheses, parentheses, and I'm going to have shift alpha Z times capital letter S divided by 2, and then squared. Okay, that should give us, where's my answer? um, that looks like an outrageously large number. Something, oh, it's still there. Okay, I got to figure out how to turn that off. That's kind of a weird, I don't like that it does that. Um, okay, so it's showing us in different, okay. So we get 126.218.219. Okay, so I'm just going to put 126.2 and I'll put dot, dot, dot. How about that? So this is going to be 126.2 dot, dot, dot. And I'm going to want to round that up to 127. All right, let's see what it's going to be on the T-Mobile side. So it's going to look the same, except here, I think on the numworks calculator, I stored this in lowercase s. So instead of hitting shift alpha, I'm just going to hit alpha like that. That's going to be divided by 2. And then I want to square it. All right, so I get 33.4. And let me do this on the Texas Instrument. So I want to copy this same formula. Okay, alpha Z times, now I need SY. That was the standard deviation of the second list. So I can hit variables. Now I'm just going to hit the number 5 to go to the statistics option, and then 6 for the standard sample standard deviation for the second list. There we go. Divided by 2 squared. 33.4. All right, so the sample size here 33.4 and some change, which we round up to 34. All right, so we got 2 answers for sample size. Now, if we were just doing Sprint all by itself, then we would want a sample size of 127. If we were doing T-Mobile all by itself, then we could get what we want, having a 95% confidence level with a margin of error of at most 2. We could get that certainty with a sample size as little as 34. But what do we do now that we want to compare these two? Well, if you want to compare these two, you could have one at 127 and another one at 34. Like survey 34 T-Mobile people and survey 127 Sprint airports. I said people, I should have said airports. Um, but another way to look at it is to look at it as, well, you want to choose the higher of the two. So that maybe you would sample 127 Sprint airports and 127 T-Mobile airports. That's another way you could do it. Um, so this represents like our rough estimate right here. All right, now remember the whole point of using a Z alpha 2 score is that we didn't have a sample size to begin with. Well, technically now we have a sample size we can work from. And so from these sample sizes, we can now calculate degrees of freedom, right? So this would be 127 minus 1. So we can have 126 degrees of freedom here, and degrees of freedom over here. We have 33. So now we can use this same similar equation to what we've got above, except now this is going to be sample size with a t-distribution. And instead of a z alpha 2, we're going to use a t alpha 2, because now we've got degrees of freedom. Like that. And then we can do that over here. Okay. We're going to still use E being equal to 2. We're going to use the same standard deviation, but now we need to calculate this T alpha 2 score, this critical T score. So I'll just do a quick sketch of our student's T distribution here. We have a confidence level of 0.95. That's the area between the two critical values. So here we're going to have a positive T critical value, and here's a negative T critical value. It's those two numbers on the number line. And we'll have a significance level divided by 2 of 0.025, which would be the area there. And an area of 0.025 is the area on the left. And so now we need to use inverse T, so like an inverse T function, to convert this area into that value. So let's do that. So over here, I'm going to go ahead and just use the native program, inverse T. Remember, this is only going to calculate area from the left. So this will give us a negative number. Okay, so we're going to put in 126 for this one on the left. So we are going to get actually two different critical values, aren't we? So we're going to get one here and a different one over there. All right, so this was instructive. All right, so we've got 126 degrees of freedom. So we're going to have a positive 1.978. Okay, so positive 1.979. All right, so here we're going to have a T alpha 2 score, 1 point, what was that? 979. All right. Um, all right. Let's leave that there for now. Um, so let me come over to the other side and on the numerics calculator, I think because I can use upper and lower case, I'm going to do maybe a lot of these calculations using the numerics calculator, I think. All right, so let me go ahead and clear what I've got just to simplify things. And let's go to the distributions. And I'm going to repeat what I just did with the Texas Instruments like that, right? Yep. And I want an area on the right, 0.025. And I want to take this value and I'm going to store that in capital letter T. Okay, now we're going to do this again, but now for T-Mobile, which has a degrees of freedom of 33. So I'm going to back out one screen, put 33, come back in, 0.025, and you can see I have a different critical score now. So now I'm going to save that, Shift X to the Y. Okay, I'm going to save that in lowercase t. All right, and that was 2.03 and some change. So the t alpha 2 came out to 2.03 and some change. And I'm going to store that in lowercase t. This one, I'm storing that in uppercase T. Okay. So now I just want to plug in um, uppercase T with uppercase S on the numerics calculator and lowercase t with a lowercase s. And that should give me my new finer estimate using the student's t distribution. All right, let's see what we get here. Um, yeah, okay. So let me come out to the calculation app and see, I need to hit parentheses a couple of times. So this is going to be the numerator. So I'm going to have shift alpha t times shift alpha s. So this is the t-score for sprint, the sample standard deviation for sprint, divided by the error, which is 2. And all of that is going to be squared, right? Um, come back. Yep, TS divided by E squared. All right. So we end up getting a value of 128.6 and some change. So 100 and did I say 128.6? 128.6 and some change. Um, so that's going to get rounded up to 129. And then over here for the T-Mobile side, so now I'm going to use lowercase t because this is what I stored the T-Mobile stuff in, times lowercase s divided by our margin of error of 2, and square that. And we get 36.0 and some change. 36.0 and some change, which should be rounded up to 37. All right. So you can see how the rough estimate, you know, gets us pretty close, but the finer estimate is just a little bit better. The rough estimate gets us pretty close, but the fine estimate gets us a little bit better to where we need to go. So I would say, this one was a little more advanced because it had more things we had to keep track of, not only on paper, but also in the calculator. But, I want to tell you again, this is the power of writing out your solutions. Okay. I'm not writing this solution down just purely for my benefit or your benefit. This is how I would just go about solving a problem myself. Because this is the only way you're going to be able to see your own mistakes, that you stored things in certain variables, um, that you draw this normal distribution and you see what you thought the distribution was. You write down all these values. Um, this is how I would write a solution to a problem. So, it's beneficial, I think, for students because it shows my thinking. Um, but when I go to study this later for an exam, I want to see what my thinking was. And the only way I can see what my thinking was is if I write it down. Okay. All right. So I think this is a good place to stop. Let me know if you have any questions.